Continuing our discussion regarding inferences for proportions, let's take a look at an actual example of constructing a confidence interval for pi. Now, it's important, if I haven't told you before, to understand that confidence intervals are always about population parameters. They're never about statistics. We use statistics to construct confidence intervals for parameter values. It's about the parameter value. It's not about the statistic. They come from statistics to estimate parameters. It's really important. Make sure that you grasp that. If you don't, sit down with the instructor and have a nice long discussion about it. All right, let's jump into an example here. Campus administration is proposing that classes which meet 4 days each week be changed such that they only meet 2 days each week, but for a longer period. The proposal suggests that would increase the number of classes available to students, allowing them to complete their degrees in less time. A survey of 137 randomly selected students was asked if they were in favor of the proposal. Of the 137 students surveyed, 114 said they were in favor. Now, estimate with 95% certainty the true proportion of students on campus who are in favor of the proposal. Well, what's this about? The administration wants to change the way classes are offered. Rather than 4 days a week or 5 days a week, want to do it 2 days a week for longer periods. So they go out and they survey a bunch of students to get an idea of what how the students feel about it. So, how many did they survey? 137. How many said they were in favor? 114. Well, 114 divided by 137, that's the proportion of yeses, correct? Okay, now, before we actually do anything, the very first thing that's extremely important is that we identify the parameter of interest. If we don't know what parameter you're trying to estimate, it's all over. You're done before you ever started. You need to understand what it is you're trying to estimate so you can go do it. If you don't, then you start mixing techniques for means and proportions and medians. It gets to be just a mess. So make sure you understand what it is you're trying to estimate to begin with. This is all about a proportion. So, confidence intervals are about estimating population parameters. What's the parameter symbol for a proportion? It's pi. You're trying to estimate pi, the true proportion. Okay, identify the probability distribution to be used, addressing all applicable assumptions and how they are satisfied. Well, if we're going to do a confidence interval for pi, then right away I know that what I want is p hat to be distributed normal. I need that normal distribution. Why? Because when we look at the confidence interval, z is right smack in the middle of that calculation. Z is a standard normal. If you're going to use a normal distribution somewhere in a calculation, you've got to justify why. Now, is it reasonable? Well, 1, I need n at least 20. Yeah, this is okay because n equals 137. 2, I need n times p hat to be at least 5. Yeah, it is, because it said that p hat equals 114 divided by n, which is, 137. So if I multiply both sides by n, which is 137, it cancels out. That's 114. 3, I need n times 1 minus p hat to be at least 5. Well, it is, because that's everybody else. So this is actually 137 minus 114, which gives me, 23? So I know that it equals 23. And I'm thinking 23 is, in fact, greater than 5. So I'm good to go. The assumptions, or right here is the assumption that I need, and all of this is justified why it's reasonable, so I can go ahead and continue with the technique. Now, I want to construct the confidence interval, and then when I'm done with it, I need to be able to interpret this thing. What does it actually mean? Well, the confidence interval will look like 114 divided by 137, that's p hat, right? Plus or minus z of alpha over 2 times the square root of 114 divided by 137 times 23 divided by 137, all divided by 137. And I'm going to change that radical to make sure you can see the whole thing is under the radical. See, 23 over 137, that's 1 minus p hat. The question is, what's this value of z? Well, if you have to do it by hand, we said 95% confidence interval, right? Well, if I'm doing a 95% confidence interval, that means up here, this value of z gives me 0.025 in the tail, which means I have 0.975 in the left tail. This is actually P 97.5. Well, if you do that in your calculator, if you use the inverse norm of 0.97501, why is it 0.1? Because it's a standard normal. You get 1.96. I'm not going to do that. You can go ahead and do it if you like. If I substitute 1.96 in there for z, these are just numbers, and I can actually go ahead and calculate the thing out. What I'm going to do instead is I'm going to go to the calculator, and I'm going to allow the calculator to handle the whole thing. So let's take a look here real quick. All right, if I go to Stat, Test, and I'm going to go down to, let's see, where is it? Right there, Option A. Option A says 1 prop z int. That means 1 proportion z interval. We're doing a confidence interval for a proportion, and we're only dealing with 1 proportion. Remember, this is about univariate. Univariate is 1 variable. And we're using a z distribution, a standard normal. So if I select it, the information, the numbers you see on the screen are the numbers I had last time I did it. For this particular problem, p hat is 114 over 137, so x is 114, n is 137. Confidence level, it said build a 95% confidence interval, right? So there it is, 0.95. Now select calculate, and there's my interval. It's saying I'm 95% certain based on this data that the true proportion is somewhere between 0.7695 and 0.8947. So the confidence interval, oops, let me change ink colors, is 0.7695 to 0.8947. So now I'm going to say I am 95% confident the true proportion of students in favor, I'm just going to say of the proposal here, is between 76.95% and 89.47%. What good is this? Well, notice that 50% is not in this interval. The lower bound is 76%. Well, 50%, above 50% would be the majority, right? Based on the data, it's saying that my minimum is like 76% with 95% certainty. There's a 5% chance I'm wrong that it could be, the true proportion could be bigger or smaller. You know, I don't know which direction, but it could be with only 5% certainty. So, because this is way above 50%, the conclusion from this is that the majority of the students are in fact in favor. Okay, that kind of wraps it up for the idea of actually constructing the confidence interval itself. One more thing I want to talk about. This is actually pretty important. Let me add a new blank slide here. Now, we just said that, as an example, we were, quote, 95% confident of yada, 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 right? Now, what gives us the ability to make that statement? Why is it that we're 95% confident? Well, here's the idea. Here's my normal distribution. For this proportion, the true proportion is the mean. It's in the middle. It's pi. We don't know what it is. We're trying to estimate it. If you go out and collect all possible samples from the population of the same size, in this case, n equals 137, and you construct a 95% confidence intervals, what you're going to get is intervals that maybe look like this. See, this would be saying I think pi is in here. Clearly, I missed. Pi is down here. You will get intervals that look more like this. You get some down here that miss. You get some like this that just barely capture pi. Some that are just dead on. Some barely capture. Yeah, it looks pretty good. Definitely got it. Okay, let me draw a line here so I can see what I'm doing better. See, all these got pi. Pi is in the interval. But I don't know where in the interval. When I construct my confidence interval, I have no idea where in the interval pi is. Or really, I don't know for sure if I even captured it. I could have had this guy. See, this guy right here missed. This guy missed. These nailed it. It's in there. I don't know which I have. But if I were to go out and get all possible samples of size 137 and construct 95% confidence intervals for all of them, then 95% of those possible confidence intervals would capture the parameter. 5% will miss. This can be proven mathematically. So, why is it you're saying you're 95% confident? Well, your confidence interval is one of these. It's one of these in here. Think of it this way. If I had 100 marbles, 95 are black, the other 5 are red, and you shake them up, and you arbitrarily reach in, randomly grab one, what's your best bet? Your best bet's a black one because 95% are black. Well, what's your best bet? You randomly went out and took a sample, you constructed a confidence interval, it's like reaching into the bucket and grabbing one randomly. 95% of them will capture the parameter, 5% are miss. It's a good bet, 95% certain, that yours will capture the parameter. Now that has additional assumptions to it, and the main assumption is that your sample is a good sample to begin with, that your sample is actually representative of the population. If it wasn't, then all bets are off. Okay, that wraps it up for this example. The next thing we need to do is take a look at sample size. If you're going to go out and collect a sample, what size should you go get? Is 137 good or is it bad? Is 30 good or is it bad? Or do we need 8,000? That's the next topic.